Hello, everyone. My name is Jinhui Qin. Today, I'm going to give an introduction to scalable computing with Dask in Python. So Python is one of the most popular programming languages these days. It is widely used by many people for analyzing data. There are some commonly used Python libraries, such as Numpy, Pandas, Scikit-Learn, for performing some data science tasks. And these are easy to understand and implement. So these libraries usually work well if the data set fits into the existing memory of your computer. But when it comes to working with a large data set using these libraries, the memory constraint sometimes could become a challenge. This is where Dask might help. So this webinar provides a brief introduction to Dask for parallel programming in Python. So basically, Dask can help Python programming from two aspects. First, to speed up your Python code execution by parallelizing some of the operations with some minor changes in your Python code. Second, to handle larger than memory data set by partitioning them into smaller chunks. So what is Dask? So from my understanding, Dask is a task graph-based framework to parallelize operations. It provides a multi-core or distributed parallel execution on larger than memory data set. It also provides Python APIs or libraries to scale Numpy, Pandas, Scikit-Learn, and etc. It can scale down to your laptop by using multiple cores on your computer, or scale up to a cluster of using multiple machines. So what Dask provides here at high level, it provides high-level data structures for data collection, for example, to mimic Numpy array or Pandas data frame, but can operate in parallel on datasets that do not fit into memory. So at low level, Dask does provide a dynamic task scheduler that can execute a task graph in parallel. To prepare to work with Dask in Python, if you just started to work with Python, it is recommended to install Anaconda, which is a Python distribution that almost includes everything you need to work with Python. That's just one of the package included in this Python distribution. You can see here, this is Dask. So some more information here says to analyze the data with the scalability and the performance, you can use Dask, Numpy, Pandas, or Numba. If you have previously worked with Python, so it is recommended to follow the install link on Dask homepage here, as you can see. Dask just an additional Python package you would like to install. You can either do conda install or do pip install. So on any Compute Canada clusters, to work with Python, it is recommended to follow these 3 steps. So you first load a Python module and then create a Python virtual environment, then active that environment. From that, you install any Python packages that you want to use for your Python work. So the detailed instruction is available on Compute Canada documentation wiki page. You just search Python, you will get there. So here is the outline for what I'm going to introduce in this webinar. So we will start to parallelize some example Python code with Dask, in specific using Dask delayed interface. This will help us to understand how Dask handles tasks in parallel. Since from the backend at low level, Dask does provide a scheduler to schedule the operations of those tasks. There are options for selecting different scheduler for tasks, which may result in different performances or for different purposes. So some general suggestion will be provided. So in addition to supporting general parallel programming in Python, Dask also provides several user interfaces, each having different sets of parallel algorithms implemented for parallel operations or distributed computing, in specific to scale Numpy, Pandas, or Scikit-Learn. For this webinar, as a brief introduction to Dask, we might only have time to demonstrate the Dask Array API for scaling Numpy array operations. So Jupyter Notebook for live code will be used for the demonstration in this webinar. So we'll start with an example as simple as we could to illustrate one of the core concepts of Dask, building graphs that describe the computation we want to perform using Python code. As you can see here, we have very simple functions defined here. The first function, inc, take a single input x and return x plus 1. The second function, add, take two inputs, x and y, and return x plus y. And both function has a time.sleep function call, so that will take a noticeable amount of time to execute, which will be very helpful for showing how Dask help us later. So let's start with the three input A, B, C, each with value 1, 2, and 3. We'll do some calculation based on this input value. We have a 3 inc function call to increment each of them, and then we have a 2 add function call, so we can add all those incrementation together to get final ABC. So you may notice that there is a time statement at the beginning of this code block with 2% sign. What it does is to measure the execution time of running this code block, so which will be very helpful when we make some changes in the code. You will see the performance changes. So okay, let's start to run this code. So as you can see, when we run a code block, there is a number showing there, which is the order in which a code block is being executed in this Jupyter Notebook. So we run the second block, and then we run the third block. So we will get the result, not just ABC, we will also get the time measurement. Okay. As you can see, the result is 9. It took like 5 seconds. Since the function call in this code block, we have total 5 function call. They are executed sequentially one by one. So pretty much you can predict the execution time, since each function call will take at least 1 second, because we call that time sleep 1 second. So the 5 seconds something pretty much what we expected. Let's take a look how Dask delay can help us here. So when you use this delayed function call, it takes a function name as input and return a delayed version of that function. So if you want to check what inc delay here, as you can see, it just say it's a delayed. So to use this delayed version of a function, so you will do the similar way as you were calling the original inc function, for example, by passing a single input attribute, like A here. You can also wrap up these two at once by wrapping up the inc function with delayed in front, and then passing in this attribute A. So let's take a look at what AI. It just say it's delayed without giving you the actual evaluation. So AI here just represents some calculation that hasn't yet been performed. So to get the actual result of AI, you will need to explicitly call the compute function. So as you can see, you get the value 2. at this point, you might be wondering what's the point of doing this delayed function call. To answer that, let's rewrite the code block that we did earlier by wrapping up all of the function call with delayed. So we can just do this. If we want to check what ABC is here, oh, here, okay, it just say delayed without giving you the actual evaluation. So ABC, same as before, it just represents some calculation, hasn't yet been evaluated. So there is a tool called Graphize. If you install that package, you call this method to visualize what included in this delayed object. As you can see, it represents as a graph here. There are some circular nodes represent the task need to be executed, and some square nodes represent the input or output of those tasks, and some direct edges or those arrows describes the dependency among those tasks. The way to read this graph is from the bottom. So we have two inc function call. The output will be input to the add function call combined with the output of another inc function call, then input to add to get the final result. So as you can see, if we have more than one core on the computer, not necessarily all of these tasks needs to be executed one by one sequentially. For example, these two inc functions can be executed at the same time, which will save at least 1 second for the execution, since each function call will take at least 1 second, right? Similar as here, the add function call and the inc function call, they can be done at the same time. That will save another second. So if we can parallelize some of the operations in this graph, so we can reduce the execution time at least 2 seconds, right? So let's check how Dask will do here. We can measure the execution time. Since we only measure a single statement execution, you only need a 1% sign in front of that time command. So if we do this, as you can see, we take about 3 seconds. It's pretty much what we expected. So now you have some idea how Dask delayed can help us for parallelize some of the operations. So here is another example which includes a for loop. So this code block just for preparing some data for this example. So as you can see, this for loop will generate a total 10 items. So each loop will create a two-dimensional Numpy array, 10,000 by 10,000, with floating 64-bit floating numbers. So X size is about 100 million numbers. So total size is about 800 megabytes. So we save that Numpy array into a binary file using this NumPy save function. So the file name is in this format. So after running this code, you will have like a 10 file saved in your disk. So I already have those data saved here. So we can check what I have earlier. As you can see, we have total 10 files saved here, and the total size is about 8 gigabytes. Okay, so what I'm going to do in this example is to calculate the summation of all those numbers saved in those files. So what you usually would do in a sequential code is you load data from each file and then calculate the summation of that file, of those data, and append it to a list of sums. At the very end, you calculate the summation of those intermediate sums you stored in the list sums to get the result. Let's run this to see what time measurement here. Okay, it takes about 9 seconds. We get the result. So let's take a look at how Dask delayed can help us here. We will do similar as we did before. We rewrite this code block by wrapping up some function call with those delayed version. So here we delay the loading data from a file. So delayed loading data here. It will return you a delayed object X. So when you call any method on a delayed object, you will automatically get another delayed object. So these statement here just append a delayed object to the list sums. So at the end, we also like to delay the final summation on this list. So if we want to check what result is, it returned the right way without giving you the exact evaluation. So result here represents some computation that hasn't yet been performed. So similar as before, we can take a look at what result here represented by using this visualize method. Okay, as you can see, this is a classic MapReduce operation. Since we have many items, we apply the same function or operation on each of them, and at the very end, we reduce all those results by applying another function to get the final result. So this is extremely parallelizable since all the operations are asynchronized. They are relatively independent from each other. So let's take a look what's the performance here. Remember previously we get about 9 seconds. So we can measure. Okay, just 6 seconds. So we see some performance improvement as this computer can run 4 concurrent threads. So we have 10 atoms. It will go like 3 rounds to get this result. So it's not linear, but you can see some performance improvement. So now you have some idea how Dask delayed interface help us for parallel some tasks. So there are 2 distinct components in Dask delayed library. The first one you call delayed function, it allows to build task graph. When you call the compute function, it executes the task in the graph according to a Dask scheduler. So there are actually options for selecting different scheduler. The one we use is just the default one. So let's take a look at what other options here. So you can see from top right corner, it's just a relatively large task graph being executed by a Dask scheduler. So in previous examples, we used the Dask delay to parallelize some computation to build a task graph instead of execute it immediately. So task just represents some function to call on some data, and the graph describes the relationship among all the tasks. So to get the result, you will need to explicitly call the compute method, which hands the task graph off to a scheduler. So the schedulers are actually responsible for running a task graph and produce a result. So here are the options. The first option is a threaded scheduler, which is also the default one when you call compute without passing in any um, parameters. Or you can pass in scheduler as threads. So what it does, it will spawn multiple threads in the same process to execute tasks in your graph. So it works well for code that spend a lot of time not executing Python code because of Python has such a policy or mechanism which is called a global interpreted logger. So what that means, it means in a single process, only allow a single thread at a time to execute Python code, to interpret and execute Python code. So if you have task workload are more rely on calling Python interpreter, so these threaded scheduler might not be a good choice since only allow a single thread at a time in one process to execute the Python code. However, if you have workload more on the I/O bound, for example, read or write to disk, or calling Numpy, Pandas, Scikit-Learn, those modules are compiled from C code. So they are not calling Python interpreter, which is also the case you saw from previous example. We call the Numpy summation function instead of writing our own summation function in Python code. So in contrast, there is another scheduler using multiple processes, which is using a pool of child process when you call compute passing in the scheduler as the processes. It works well for code that spend a lot of time interpreting and executing Python code, because each process has its own Python interpreter. In this case, you have multiple processes executing the code. So however, it takes longer time to start up multiple processes than start up multiple threads, because the process usually has a lot more overhead to maintain than those threads. So which one to use is really depend on what kind of workload you have or what kind of code you have. So the third one is a single thread. So in this case, you're passing in the compute with scheduler as a single threaded. So it will be useful for debugging purpose since the code will be executed sequentially without any parallel. So the last one is the distributed scheduler, which uses a pool of worker processes along with a scheduler process. It will be very useful if you have a very large workload and most of the operations are asynchronous. That means that they are relatively independent from each other. So you can use it on a single machine or scale out to many machines. So, but before you are able to use a distributed scheduler, there are some advanced setup you will need to do before you can use such a distributed scheduler. So I'll provide some more information about how to set up a distributed scheduler. So the first thing you will need to do is deploy a Dask cluster that consists of a single centralized scheduler and one or more worker processes. So how to deploy a Dask cluster? First, you will need to launch a Dask scheduler process on one of the nodes on the cluster, and then launch several Dask worker processes, possibly on different nodes. You can launch all of the worker processes on the same node as the scheduler process node. So in that way, you just running a Dask cluster on a single node as a local clusters. So that also works. So here is an example to show how to manually deploy such a Dask cluster with 4 nodes from command line. So first thing, you launch a Dask scheduler on one of the nodes by running the command Dask scheduler. Once the process is started, it will provide information about the IP address and the port number on which this scheduler is running on. Then on rest of the other node, you run this Dask worker process by providing the IP address and the port number of this scheduler. After a worker process is running, it will give you the message to tell the worker process IP and port number, and also says it registered to this specific scheduler. So you run these commands on each of the other nodes you would like to run the worker processes. So Dask scheduler and the Dask worker are Python executable that included in Dask distributed package. These processes are running at backend like daemon processes on a Dask cluster. This is the most fundamental way to deploy Dask on multiple machines. In a production environment, these processes are often automated by some other resource manager. So on Gram or CEDA, those Compute Canada clusters, these processes, however, needs to be manually launched on each of the nodes that you requested from your Slurm job submission script to construct your own Dask cluster. So thanks, Dask also provides such a tool called Dask MPI, which will be very helpful when you work on Compute Canada clusters. So, or on any HPC clusters where all the nodes, all the compute nodes are sharing or facing the same shared network file system. So you can use this tool called the Dask MPI to deploy such a Dask cluster. So here just some example information you would like to include in your Slurm script. The top part here just specify how many nodes, what kind of node, and you would like to request from the clusters. And after you have this resource available, the first thing you will need to do is activate your Python virtual environment, assuming you have those Dask package, including this Dask MPI tool, or installed, pre-installed in this Python environment. Then you use srun to launch your Dask MPI tool. What this tool does is to launch a Dask scheduler first on one of the nodes you requested, and then launch a worker process on each of the other nodes you requested. So when a scheduler process is running on one of nodes, it will write the IP address and the port number of that node into this empty file you provided. So then later when launch the worker process can read data, the information written by the scheduler from this file. So they know where to register with that scheduler. It is also a good practice to provide a local directory with this Slurm environment variable here, because once you have such a Dask cluster running, so all those worker process and the scheduler process will spit out some temporary data. So if you provide this local directory for each node, so those temporal data will get written into this local directory without affecting the rest of a shared file system. You can also provide many other options, for example, to specify how many threads you would like each worker process to run, and how large the memory you would like each worker process to use. So there are many other options. So after those Dask workers are launched and registered with the Dask scheduler, the Dask scheduler is aware of how many workers and how many cores that each worker is running on. Once you feed a task graph to this Dask scheduler, it will be executed using all of the cores that have been registered to the Dask scheduler by those Dask workers. So, okay, after you have such a Dask cluster deployed, how to feed a task graph to the scheduler in your Python code? So to use distributed cluster to compute your Dask graph, the first thing you will need to do in your Python code is to create a client instance to connect to the Dask scheduler. There are multiple ways of doing that. So for example, here you can provide a specific IP address and port number of the scheduler when you create such a client instance. Or you can simply just provide the scheduler file that you used when you deploy that Dask cluster. So in this way, a client is connected to the Dask scheduler. The second thing is to feed the workload to the scheduler. So there are also multiple ways. So for example, here, the submit function call, you can use it to submit individual asynchronous tasks. Or you can use the map function, or simply use the compute with some tasks. Since you are feeding workload to a clusters, they are not going to return to you the result right away. So instead, it will return a future object. So to get the result, you will need to explicitly call this gather function by passing in those future objects to get the result. So okay, this is the most fundamental way of set up a Dask cluster and use the distributed scheduler. If you are just getting started, Dask does not require any setup if you only want to use it on a single computer. If you would like to learn more about Dask deployment on a variety of distributed environment, here is a link you can check out the documentation provided by Dask. So for example, Dask also supports like Kubernetes or Hadoop. Yeah, there are different setups there. So in addition to support general parallel programming in Python using Dask delayed, as we saw in the previous examples, Dask also provides APIs which have parallel algorithm implemented for parallel operations or distributed operating on large data collections. So let's take a look how Dask Array for scaling Numpy array operation. So Dask Array provides a parallel larger than memory and dimensional array using blocked algorithm. It uses all of the cores on your computer to parallelize some of the operations. It breaks up a large array into smaller pieces to handle larger than memory dataset. Instead of performing a large computation, it performs many smaller computations by implementing some blocked algorithms. So here are the documentation and the API reference if you can check out. So let's take a look. This is a simple example to show how a blocked algorithm worked. So we have some data set called random.hdf5 stored under a directory data in this computer. So HDF5 is a data format for storing and organizing large amount of data, for example, multi-terabytes of data on disk. So H5Py here is a Python package to provide a Python interface for accessing this type of data on disk. And you can easily manipulate that data from Numpy. For example, you can slice into multi-terabyte data set stored on disk as if they were real Numpy array. Or you can iterate over the data set in a file to check out the shape, the data type, those attributes of the data set. So here F is just a file pointer to that file. So dset is the access to the data set pointed by this file pointer F. So if we want to check what dset here, as you can see, it says it's a HDF5 data set. So the shape of the data is a one-dimensional in 1 followed by 9 zeros. So that's a 1 billion numbers. So the type is 4 byte floating. So the size of this data set is about 4 gig, right? We can actually check what's the data set size here. So as you can see, this file has about 4 gigabytes. So what we want to do in this example, similar as before, we want to calculate the summation of the entire numbers in that data set. Since that will require you, if you load the entire data set into your machine, you will need at least 4 gig of memory on your computer. So instead, normally you take chunk of that data set at a time and calculate the summation, and then append those summation of the chunk to the list sums. At the very end, you calculate the total summation of those intermediate sums. So after you iterate over the entire data set. So here, each chunk we have like 1 million numbers. So you will have ended up with total 1,000 loops for calculating the entire summation of this 1 billion numbers, right? So we can run that. Okay, this is how you usually will do by implementing the blocked algorithm yourself in a sequential code. So using Dask Array, it has all these blocked algorithms implemented for handling large data sets. So Dask Array is a NumPy-like library to operate on large data sets that do not fit into memory. It extended to n-dimensional algorithm and provide a subset of the NumPy interface. So that means not all of the function available for the NumPy array will be available in Dask Array. Some of them is not implemented yet. So you can create a Dask Array object from any NumPy array object with this function called the from array function. It will take like 2 attributes, data and the chunks. So any object that supports NumPy style slicing, for example, previous the data set called dset, you can pass in as the data attribute. And also you will need to provide a chunk size to tell how to partition the array. For example, previously we take every a million number as a chunk. So you just provide the chunks also as a one-dimensional NumPy array here. So if you would like to check what X is, it says it's an array with the size of 4 gigabytes. It has a total 1,000 chunks. So each chunk is 4 megabytes because each chunk has 1 million numbers. So each number is 4 bytes, right? Okay, that's how the Dask array partitioning a Numpy array. So then you can manipulate the Dask array object the similar way as you would on a Numpy array. What does that mean? That means we can perform standard NumPy style computation like arithmetic, mathematics, slicing, reduction, and etc. on a Dask array. The interface is familiar, but the actual work is different. The difference is that any operation on a Dask array are lazy evaluate. It doesn't do the computation immediately as it does on a Numpy array. What it does is to split the array of data into chunks based on the provided chunk size. So to calculate the sum of the Dask array, you would do the similar way as you would on a Numpy array, just call the sum function. But it didn't give you the result right way. It says it has a total like 2,000 something tasks need to be done for calculation. It just represents some task graphs here. So if you want to take a look what it looks like here, we can use previous method to visualize what it looks like. Since it will be a very large task graph, we have for total 2,000 something tasks. So even for build this graph will take some time. It says graph is too large. So but we'll see if we can do this. Yeah. So you can see here, it's a very large graph, but they organized already into like a 4 chunk as a group, since this computer can run 4 concurrent threads. So this is the way how Dask already like organize these task graph into parallel. So to get the actual evaluation, you will need to call the compute explicitly. For example, you do sum, but you will need to call the compute to get the result. C. Another advantage of this is if you want to calculate some other values on this array, you can just using the tab key on your keyboard to find a list of available method you can use. So for example, standard deviation or some other operations. So the similar way as you would do on a Numpy array. So here I will just show you an example to demonstrate the performance of a Dask array here. So using Numpy array, for this example, it generates a 2-dimensional Numpy array, 20,000 by 20,000 with normal distributed random numbers. So total you will have 400 million numbers for this array X. So each number is 8 byte floating number. So total this array size is 3.2 gigabyte. So to calculate the mean or average of this X based on the axis 0, that means you're doing column-wise the average, and then take every 100th element from that result. So to run this code, you will need at least 3.2 gigabyte of memory, right? So let's see what's the result you get here. See, it took 11 seconds something, you get the result, right? So using NumPy, it needs gigabytes of memory and take more than 10 seconds. Let's take a look how Dask Array handle this. As you can see, when you create a Dask Array, the interface is very similar to the NumPy array interface for creating such a two-dimensional array. The only difference is here you need to provide an additional attribute called chunks. So here we have a chunk as a two-dimensional array, 1,000 by 1,000. So that means you will cut into this original 20,000 by 20,000 array into 20 by 20 chunks. And then each chunk is 1,000 by 1,000, so that's 1 million numbers. So each chunk is about 8 megabytes. So then you calculate the mean, similar as before, along the axis 0. So you do column-wise the average, and then you do the compute. So let's run the code to see what we have, the result here. So you only take 3 seconds to get the result. So the difference is here, you only need at least megabytes of memory. For example, because each chunk is only 8 megabytes. So if we can run 4 such a chunk at a time, so you will need a maximum like 32 megabytes of memory for handle these kind of calculations. And also you got a better runtime. So this is how Dask Array can help you handle large memory data set by scale down to using multiple cores on your computer and split up the large data set into smaller chunks. So before you start to do any work using Dask, it is strongly recommended you take a look at the best practice provided in this page. So it gives you some good advices for what you should do, what you should not do. For example, how to select a good chunk size and chunk shapes. So if, for example, you provide a chunk size is too small, you ended up partitioning your data set into too many chunks. The overhead sometimes will kill the performance gain. And there are also some information, for example, how to write your own operation for doing block-wise operations and etc. So if you check Dask Array documentation at this page, so here are the available NumPy interface you can do in Dask Array. But the limitations is also here. Some linear algebra function is available, but a lot of them hasn't yet been implemented. So this is because Dask development is driven by immediate needs. So some less used function haven't yet been implemented. So it encourages any community contributions. So if you want to look at the entire Dask Array API, you can just follow the link provided here. So, okay. I don't think we have time to show the Dask data frame. So this just some really good reference and documentations if you want to work with Dask in Python. So they provided some best practice for each interface. You can go check out those. And some really good helpful examples also provided for different applications or different area you would like to work. So if you have any question would like to ask about Dask, so here has some community links. You can go follow some forums. Yeah, that's all for this webinar. I will just stop here.